Hello everyone. I have so much to talk about, so I'm just going to jump right in. Before I can talk about the planets that I've been following up over the last couple of years, I would like to first introduce the survey that made the study possible, which is TKS, or the TESS Keck survey, or TKS. We heard a great talk yesterday by another TKS graduate student, Joey Murphy at UC Santa Cruz, but very briefly, in case you were not there or did not get a chance to see his talk yet, TKS is a very large collaboration amongst partner Keck institutions. Collectively, we were awarded more than 100 nights over 4 semesters using high-res on Keck 1 telescope to confirm and characterize TESS planets. Now, in terms of science, we have already collected a number of single system publications at various stages in their lives. A lot of our earlier work, TKS 1 through 4, has already been accepted and published. As Joey pointed out in his talk, there are a lot of numbers missing between 4 and 10, but I can assure you they're not missing, they're just going through the process. And then finally, we do have some still in their earlier stages. In fact, for this special system, TUI 1246, another TKS grad student, Emma Turtleboom at UC Berkeley, is presenting a beautiful poster on this system, so I'll let you go visit her, and she can tell you why it's awesome. But now for ensemble catalogs, it's a bit of a different story. For starters, it's still early, and we all know that catalogs take a lot of energy and time. But also, a lot of the catalog level products from TKS are being led by more junior scientists within the collaboration. A perfect example is Joey Murphy, who we saw yesterday, is talking about, now I went backwards, about population level atmospheric prospects. However, I am pleased to say that we recently submitted our first in the series of ensemble analyses, or the 0th paper out of the survey. As you can see by the title, this lays out the science motivations for TKS and ultimately why we selected the sample that we did. But because this is a TESS science conference, people want to hear about science, I'm not going to bore you with the vetting and selection steps, but refer you to the paper if you want some clarifications there. The one thing I did want to point out is that the paper highlights the importance of reproducible populations, with a particular emphasis on RV surveys, since this has been a major limitation for exoplanet demographics. So often we might drop a target that has a stellar or substellar companion, rapid rotation, high activity levels that would require GP processing to disentangle the signal. Of course, this is fine, but it's made survey selection functions extremely difficult to reproduce in later studies. So anyway, we came up with this idea for an algorithm. We implemented it, and how did we do? So this figure is showing a lot. I'll break it down for you. The top 2 panels are stellar properties. The bottom 2 panels are planet properties. The top left is an HR diagram. The top right is in stellar mass metallicity space. And then the bottom 2 are the planet size on the y-axis, and then period and incident flux space on the x-axis. So we started with a fully observable TOI sample in gray. TOIs for which we grabbed a recon spectrum and it passed all of our various vetting and selection steps is shown in black. So specifically, these targets were available during the target selection process. And then finally, we have our selected sample shown in orange. So what is this saying? Well, even with 100 nights, we still wouldn't be able to go out and measure awesome masses for all of these targets. But that doesn't mean that they're not great targets. So I'm hoping the paper could be used as a reference to identify other promising targets that might hit more specific science interests, or something just not directly related to TKS at all. So Joey briefly discussed this yesterday, but TKS is broken down into 4 main science themes. So now let's take a look at only the TKS sample, split up by its 4 science themes over the same parameter spaces. So concentric rings demonstrate targets that were selected by multiple programs. And if we look at the numbers, you can see there is an enormous amount of overlap between 3 of the 4 main science cases. So as I previously alluded to, we implemented a unique algorithm to strategically select the optimal target sample given the various science goals and telescope allocations. And this is a beautiful demonstration, rather proof of concept, of the unique target selection that we implemented. So now for the rest of my talk, I will be focusing on this guy over here, which has essentially little to no overlap with the rest of the as targets, and you can visually see that it's an outlier in many parameter spaces. But to start with some motivation, I wanted to show this great figure from a 2018 review by Rebecca Dawson and John Johnson discussing the origin of hot Jupiters, one of the first ever planet types to be discovered, and it still stumps us to this day. Where did they come from? How did they get there? And in particular, I really like this table because it synthesized all of the information, literally decades worth of work, into a single table. So the table columns have the three main popular hypotheses of hot Jupiter formation, which is in situ formation, ex situ formation and migration, inward migration, disk migration, and then high eccentricity or tidal migration. You can see that some of them, they each have their strengths and weaknesses, but the caveat is that there's no single great answer for the entire observed population of hot Jupiters. And one of the main takeaways from this table, or at least what I took out of this, is that stellar ages might help here. And this is where our program comes in. So the subgiant branch is a rapid phase in stellar evolution. So a location on an HR diagram gives us a really precise, not only age, but also mass, which is really helpful for characterizing these systems. But because they're more evolved or a little bit larger, we'll also be biased towards larger planets, so that actually might help inform some of these theories. But to test our hypothesis, we characterized all the TOIs using isoclassify to determine their ages, and I plotted the histograms of the fractional age uncertainties, I think up through TOI 2500. This was done a little bit ago. So not unexpectedly, we see fractional age uncertainties all over the place, but if we strictly limit it to the stars in our sample, you can see it looks much better. So that was a great sanity check. So anyways, enough about the ages. What does the sample look like? So here's the program sample in an HR diagram on the left and planet radius incident flux space on the right. Markers are colored by their mass significance. What I mean by this is the darker the marker, basically the better the mass. And then additional planets that we found as part of this survey that are not TOIs, non-transiting, are shown in orange. And for these, I just used a basic mass radius relation to get a rough planet radius, but I'll show the masses later. Now, mind you, keep in mind, I have more planets than time to highlight, so I'm going to zip through some of my favorites at the moment. I'd like to emphasize that there are also a lot of other fascinating systems in the sample. So for each of these systems, I will highlight them on the population level, show our current data for this system, and then highlight some of the unique characteristics. And the first is my personal favorite, TOI 2145. Right away, you can see the star is quite massive and young-ish. In fact, it's pretty metal rich, so it's even more massive than the solar tracks that I have there for reference let on. Now the planet is also enormously massive. I was about to call it a hot Jupiter, but then I just realized it's technically, I guess, falls in the warm Jupiter regime. Regardless, close and massive planets around massive stars are incredibly rare. Not only that, but there is also a probable close planetary companion, and you can see that in the fit and near a 2-to-1 resonance there. So I'm still trying to wrap my head around this. But moving on, the next TOI I'll talk about is TOI 1736. This one is much older than the previous one, actually an older solar-ish like star. I keep saying ish. So the system initially confounded me because there were a lot of TCE and DV reports generated for this small transiting planet candidate, but I noticed they all had roughly the same period. So the obvious thing to me was like, oh, is this a TTV system? I showed it to others in TKS and everything seemed to check out, so we just decided to follow it up. Lo and behold, there's a massive outer companion where we managed to get peri-passage thanks to the Automated Planet Finder, APF, but we're still trying to nail down the period. And it's also worth noting that there are a lot of periodicities present in the residual time series data. I don't know if this TTV systems are not really my jam, so I don't know if this is common, but regardless, it's a super interesting system. Okay, so we've had our hot, warm super Jupiter, a cold super Jupiter. Now let's switch to an eccentric hot Jupiter. This is also an older solar-like star, but here we have a significantly eccentric hot Jupiter. As you can see, there is a significant trend here, but it's definitely not as well fleshed out. But it's still quite interesting given the eccentric hot Jupiter. And I don't want to spend too much time here because I still have one more system to highlight and I'm running out of time. So TOI 1898 is actually a funny story. You can see that early on in the time series. It's actually being followed up with APF, courtesy of Paul Dalba, a postdoc, a TCAS postdoc who's been working a lot with the single transiting planet candidates. At the time, I didn't know this, and I started also following it up with HiRes, and then we just were like, hey, we're both following up the same thing, and the two together, which kind of saved the day and rescued the period for the single transiting candidate. However, I don't know if you see this, but something else is going on in the residual fits where you can, I don't know, I've just highlighted a few points. It just wasn't adding up. And I thought we were getting the period wrong because we only did have the one transit. However, when we injected another planet, it seemed to do a pretty good job describing the system. And because of the extended baseline and additional phase coverage the APF gave us, we were able to get a 3 sigma mass constraint on the planet that's at roughly 2 times the period of the inner. So this one was interesting to me because eccentric warm Jupiters are good for high eccentricity migration theories, but the somewhat close companion is not. And the opposite is true for the in situ formation or ex situ formation migration scenario, at least with one having a significantly non-zero eccentricity. So anyway, we still need more observations. We have this wonderful sample of planetary systems that come in all different shapes and sizes. We have stellar ages, we have precise stellar ages, we have a wide range of stellar masses, and the idea is that first we'll compare these to main sequence and red giant planet populations, but also because we have such a nice diversity of systems with large planets, we can revisit things like what I had discussed earlier about hot Jupiter formation and migration, and maybe even tie in those ages to better constrain some of the dynamical timescales over which these processes occur. The one thing I did want to say is the unique thing about our program is that we aren't just following these up for confirmation, we are continuing to follow these up today. So we're probing long-term characteristics in these systems, therefore sensitive to the eccentricities in the systems, multiplicities of the systems. So stay tuned. I'm currently working on the catalog paper, and with that, I will leave up the figure from my TCAS Evolve. Oh yeah, again, we have more fun systems in there and some small ones too. As I said before, I encourage everyone to check out the TKS paper. And then finally, I will shamelessly use this space as a plugin for something completely unrelated, since this is precisely the type of audience we would hope will use it, which is new open source astroseismology that hit the archive yesterday. And the code was calibrated with wonderful space-based photometry missions like TESS, so it's already ready to go. Please see me if you have any questions about that. Thank you so much. Sorry for going over on time.